old school expectation value. Okay, but this was for a pure state. For a mixed state, let me now jump to the mixed state, and then I will talk about what's a mixed state. Okay, so the way you go about for a mixed state is, so this is the mixed state. This is my Scratchpad. Better written version is available to you. If it's a mixed state, what you are doing is you are taking these pure states. I now put a label to it. I will need a bunch of them. And I'm adding them incoherently. Okay, from 1 to some number. I will call it m. Okay, so this is so-called statistical weight. It's an this is an incoherent sum. Okay, so this is a so-called statistical mixture. So these weights, they are real numbers, less than 1, and they should add up to 1. So this is like a pie chart. There is, like, let's say 10% of this pure state, this much of that pure state. All of them should add up to 1. Okay, so these guys. Okay, we are back. So this is a statistical mixture. If this m is larger than 1, that means you have a mixture. So for this, we have a mixed state. If you have only a single summation, then P has to be 1. Then it's a pure state. So m equal to 1, it's a pure state, otherwise mixed state. Let me just show, this is again something important at the very center of this business, coherence. If I want to show you that this is an incoherent sum. A coherent sum is like a superposition principle. So if I take C1, psi1, and C2, psi2, and then if I call this my state psi, which is a pure state still, and if I calculate its outer product, which is the density operator, then I will have cross terms. So let's write also this guy, bra, which is C1 star, C2 star, psi 2. Okay, in that case, I will have mod C1 squared, this guy, plus mod C2 squared, the other guy, plus, so if these were the guys, then I would get this statistical mixture. But thanks to these cross terms, when just multiply out this, you also have cross terms, which is twice the real part of C1, C2 star, and one of these guys. So, let me write it in full form. So C1 star, C2 plus permutation conjugate. Okay, so this is the this guy. So if you cannot preserve the phase coherence between these states, then these terms are scrambled, so you are left with statistical mixture. So that is the difference between a coherent sum and incoherent sum. Okay, a quantum computer should preserve these coherences as much as possible to the circuit depth. So if you have a quantum algorithm that runs for 20 gates, then throughout those 20 gates, you must preserve these coherences and also coherences in entangled qubits as well. Okay, then let me just see what I should mention. I guess the most important part in the notes, you see some other simple example. Okay, which you can take a look. Also, another important thing is if you give somebody a density operator or density matrix, how would you know if it is a mixed state or a pure state? It is very easy to test. The thing you have to do, by the way, the trace of this guy must be 1. It's a normalization. It's a probability. So this must be 1. And for pure state, mixed state, it is always 1. Thanks to this statistical weights adding up to 1, it's 1 for either case. But the rho squared, the trace of rho squared, is it 1? That is the checkpoint. So if this is 1, then this is a pure state. If this is less than 1, rho squared, trace. If it is less than 1, it cannot be larger than 1, then it's a mixed state. This is for a qubit, okay, for 2 dimension, for d equal to 2. For dimensionality larger than 2, you have to also check trace cube, rho cube. Is it 1 or not? Okay. So it's very easy to test. Take your rho, take its square for qubits, and for qubit, qubit, whatever, just rho cube is sufficient. You can check whether it's pure state or a mixed state. For mixed states, there is some, as a jargon, you should know this, maximally mixed state. Maximally mixed state. Okay. In that case, for a maximally mixed state, the density operator has equal weights. So this is a very democratic country. All these guys, they have equal contributions in the mixture. So that is called maximally mixed state. So for dimensionality D, all of them grab their fair share. So it is, sorry, my dummy variable, let me call it n. Okay, from 1 to the dimensionality n. So this is a maximally mixed state. Okay, for a maximally mixed state, there is no information you can get out of it. Okay, if you are in a maximally mixed qubit state, okay, so your qubit is maximally mixed, then you make some measurements, some photon polarization measurements along horizontal or along vertical direction, or left or right or whatever, A, D, whatever. For all these guys, it's 0. It's unpolarized. So you have an unpolarized system, okay? It is the limiting case. Maximum mixed state is the limiting case of a thermal ensemble. A thermal ensemble is the another mixed state. In here, you have your energy states, and your energy states are populated with the Boltzmann factor. So this is state EI, whatever, and the statistical mixture in the thermal state is over those eigenstates. Say these are discrete, okay? and the weight is the Boltzmann factor. So 1 over kBt beta energy divided by normalization purposes, the partition function and the energy basis. This is a thermal state. So states that are lower in energy, they are further populated like a thermal system. Okay. And if you really let temperature go to infinity, in that case, all these states will be equally populated. So it will become a maximally mixed state. Okay. In quantum optics, thermal and maximally mixed states, they arise very commonly. Now, in the lecture notes, you will see what are the properties of density matrices. Trace is one, and for the rho squared, if it's a qubit, it can be 1 or less than 1 if it is pure or mixed. By the way, this test that I mentioned here, in the lecture notes, you also see von Neumann entropy version of this as well. Okay, so you can also check whether your state is mixed or not by calculating the entropy. But trace is something very cheap, and that's why this is easier to do. Now, the point is, how do those mixed states arise? Okay. What is the underlying reason behind mixed states? So the point is, I have a system. This is my quantum computer or my measurement device, a quantum measurement device. Okay, and if this system is isolated, it will stay in that prepared pure state. Okay, but in general, you cannot isolate your systems, quantum system, whether it's a defect center, it's in contact with the lattice vibrations, phonons, or I will give you a photonic example as well. You cannot isolate a quantum system. So it is in contact with environment, a reservoir, a large degree of freedom. Okay, this reservoir has too many, Avogadro number of molecules in this room, whatever, or phonon vibrations, whatever. So you cannot track this system. But this is an easy one. You can keep track of this guy. So if these are in contact because of some interaction, okay, some Hamiltonian that links your system degree of freedom to the reservoir degree of freedom, then you have this mixed state business. It comes about through this. Your reservoir is in another pure state, actually. Okay, say your reservoir is in some state EI. Let me see. Reservoir SRC reservoir and reservoir. Okay, such a anyway. Shall I leave it like this? Or yeah, let me just give you the story, then I will give you a concrete example. So what happens is that when the system starts, when you just connect your pure system to a reservoir, they first start like separable states, tensor product states. So let me write this as simply as reservoir states like this. At time t equal to 0, this is your density matrix. This tensor product means they don't talk to each other. Okay, and then as this thing cranks, there will be information flow, and these states will know about each other. and what you will have is an entangled state. Your system degree of freedom will be entangled with the reservoir degree of freedom. It is inseparable. That is the meaning of entangled state. You cannot write your composite system as a product. Then it is entangled. Okay, and this interaction makes this connection. Physics is interactions. Physics is the study of interactions. So that's, once again, interaction playing a role here. So now here's my example. This example is not in the lecture notes, but I think I find this example very simple, but very convincing. So I take a qubit. My qubit is a two-level system, like a laser, whatever, just the excited state and ground state of a three-level laser. I just consider these two states. So this is the excited state. This is the ground state. And my electron is inverted in the excited state. So this is my system, okay, this S guy. Now, I put my atom in this configuration. I invert my system and I put it in vacuum. There is nothing around, only a vacuum. You can put these mirrors or there are no mirrors. It is just all the full cosmos, whatever. But as we know from Sabih Hoca's lecture, vacuum is not vacuum. Vacuum has fluctuations. Meaning there are zero photons here. Okay, no photons. I don't excite the system. However, as you know, Sabih Hoca mentioned, it's like a harmonic oscillator, and for a harmonic oscillator, you cannot have a particle that stays like this. This is violating uncertainty principle. So it has to fluctuate. Okay. So electric fields, magnetic fields, they have to fluctuate with zero mean, but their variances are non-zero. It's the takeaway message of Sabih Hoca's lecture. So we have, to begin with, an electron in the excited state, and there are zero photons in the universe. If this decays to the ground state, it will emit a photon, and there will be one photon in the universe. Okay. So this decay rate is so-called spontaneous emission. Okay. So spontaneous emission is is like an oscillator, excited state, ground state. It's like a dipole. This atom is like a dipole. It has a dipole moment, electric dipole moment. So it can couple to an electric field of even vacuum. And vacuum is fluctuating. So it can, and it does, with some probability, decay. It is called spontaneous decay. What we have is a state like this. You are either in the excited state and there are zero photons in the universe with this non-decay rate. Let me call this, so probability is square of this. Let me call this P. Okay, so probability is gamma squared. Okay, plus, so this is the probability of no decay. And there's a probability of decay of your electron in the ground state, and one photon has left the system. Okay, so this is now because of this interaction, spontaneous emission. So that spontaneous emission is this coupling. Wigner-Weisskopf did this historic calculation even before quantum electrodynamics was around. Then quantum optics came with much easier technology. You don't need QED to learn quantum optics, as Sabi Hoca very easily introduced. So this is our state, okay? This is our atomic photonic state. It's a pure state. It's the universe, okay? It is all this wave function. It is all this wave function. It's a pure state. Universe is pure. But if you just concentrate on, if you just keep track of the system degree of freedom, you are ignorant about the reservoir degree of freedom, which you cannot keep track of. But doing so, you are causing entropy and you are causing statistical mixture in your knowledge. Okay, so what you are doing is we just care about the atomic degree of freedom. How do we do this? We trace out the reservoir degree of freedom of this composite system. I'm using now photonic, so I should say P. Okay. So that's very easy to do. How do you trace out a composite system? It's just 0 and 1 photon for the reservoir degrees of freedom. Okay, you just sum over all those diagonal entries. So you just make this density matrix or operator like this, and then you calculate this guy 0. Let me just write this as rho AP plus 1. So this is 1. Okay, so this is the trace over the photonic degrees of freedom. Okay, I get this, unfortunately. Okay, sorry for this. So let's just do this. So what you will have is those cross terms. I think I have erased out some 1 minus P here. Okay. When you do this, let me first write this state E and square. This is these are the P squares. By the way, I think I have a squaring problem here. I guess, yeah, I guess P is just without the square. But anyway, so now we have a square. Okay, and there is this ground state, and if you like, there are tensor products here, notationally. These are the diagonal terms, and then there are off-diagonal terms, 1 minus PP, EG, and 0, 1, and Hermitian conjugate of this. Okay. Now, if you take this and take these photonic matrix elements, then because of these guys, okay. So if you just sandwich this between 0, 0, this is non-zero. But if you sandwich this between 0, 0, this is orthogonal and this is 0. And so is this. So only these two terms will contribute. So when those two terms contribute, we have the statistical mixture. Okay, 1 minus P squared EE plus P squared GG. Okay, so this is your mixed state. of the atom. When you are ignorant about the decay, okay, which is you cannot prohibit this unless there is something called a Purcell effect. With Purcell effect, you can reject this photon. Okay, you can design your cavity such that photon is persona non grata. You do not let it survive in your system. In that case, you can cope with spontaneous emission. Okay, so the takeaway message is statistical mixtures is just because you are not protecting your system from the environment. Okay, so your system degree of freedom is being entangled with the environment, and you are not keeping track of the environment. So only the system subspace is now half of the story. Okay. Now, in general, since this density operator is so important in this business, there is something called quantum state tomography. So, what is a quantum state tomography? If you have an unknown density operator, how do you learn it? By experiments. So it's an experimental technique, but it's very expensive. Quantum state tomography is very expensive. Why is that so? First of all, for an unknown quantum state, there is the so-called no cloning theorem. So no cloning theorem just tells you that you cannot form a replica of a quantum system, okay, unknown quantum system. Okay, so for quantum state tomography to work, you need multiple an ensemble of that quantum state. So it's kind of an oxymoron, right? If it's a single copy, you cannot do tomography because of no cloning theorem. So single copy of a quantum system, no way. But usually this is the context. You have an experimental setup. You initialize your system, okay? You initialize your system. You run your system. You get an output. And you can run this many times. So in this scenario, you can generate that quantum state or that process, let's say, repeatedly, okay? So in this context, what you are doing is you have multiple copies of these states prepared, okay? And quantum state tomography is identifying, or in a sense, it is estimating the entries of this density matrix, okay? So these are all estimates of the entries. So you have a tolerance, and within that tolerance, you can come close to, say, to the exact value of these entries. But as I said, experimental people, they do tomography when it is really heavily needed. In the lecture notes, I have an example for mixed state tomography and pure state tomography. For those examples, there is something called mutually unbiased basis concept. You can read about this since because of some delay, I think I will leave this mutual unbiased basis for you to read. And there are two homework assignments in the lecture notes for you to actually extract for a photonic qubit the Stokes parameters. So The Stokes parameters, it's a classical physics concept. Engineers know this. There's something called Poincare sphere, and an electromagnetic wave on this Poincare sphere the polarization of the electromagnetic field, if it is circularly polarized, right circularly polarized, it is this pole, or left circularly polarized, the south pole, and all of these on the equator, they are linear polarization. These guys are elliptic polarization. So this is the Poincare sphere, and these Stokes parameter S0, S1, S2, S3, knowing this actually, by the way, this is always one, but S1, S2, S3, those three parameters allow you to spot you on this Poincare sphere. When this quantum information took over, all of these were, used also in Bloch sphere analogy, and it is one-to-one actually. You have these mutual unbiased bases like the horizontal and vertical and diagonal, anti-diagonal bases. By the way, am I? Sorry for this. This is the vertical basis. This is A. This is D. Whatever. Okay. So given any density matrix for qubits, you can always write this in terms of these Stokes parameters. Stokes parameter times the Pauli spin matrix, or the Pauli operator. Pauli gates in quantum computation. Okay, so any density operator can be expressed in terms of these Stokes parameters. So quantum state tomography, in a sense, using multiple measurements, tries to extract these Stokes parameters. So, for instance, let me write the Stokes parameters in terms of these expectation values. So, Stokes parameter 1 is this polarization difference between horizontal and vertical. That means your quantum state rho horizontal minus vertical expectations. So if you want to extract this S1 parameter, you must do so many measurements to get this Stokes parameter as precisely as possible. So because it's a probabilistic measurement, each time you get a different result, you must sum all those. So I give you a mixed state and a pure state examples for you to play around with density matrices. And once you can extract these Stokes parameters, that means you know you have recovered your density matrix, density operator. Okay. Any questions so far? I hope I'm still in the Zoom.
Hello, is there anybody else who wants to ask a question? Any questions? No question?
Okay, so I'll then switch gears because of time limitation. Now, I will then talk about, again, these are in the lecture notes. Let me just show you. These are the things in the lecture notes. Some of them I covered, some of them I left you for you to go through these. Okay. Now, again, Sabih Hoca talked about squeeze states, let me also run through my lecture notes on squeeze states. because it's quite important in quantum optics and also in quantum information. So to repeat, if you have two observables like quadratures, phase quadratures x1, x2, and if they do not commute, then their simultaneous measurements are under this Heisenberg uncertainty relation. Okay, so Sabi Hoca mentioned these quadratures x1, x2, and he derived actually these variances. Okay, so here is the plot of the standard deviation x2 and standard deviation x1, and this line, red line, is Heisenberg limit. So in general, a quantum state is somewhere here, okay? A coherent state is just on that limit, and it has equal errors in each quadrature. It's very democratic. You cannot reach to this region. This is quantum mechanically forbidden region, okay? Now, if you are below this line, then in this shaded region, you have less uncertainty in x2 quadrature. You have squeezed your uncertainty at the expense of a larger uncertainty in x1. Okay, so their product cannot beat this. Only for the coherent state or only on this line, you can enjoy the minimum uncertainty. How do you do this squeezing? Is this operator. Okay, so this operator is the squeezing operator, and it looks like a monster, but you should be psychologically prepared. Anything in quantum mechanics, any useful object is some e to power a business. Okay, it's a unitary operation, or like a squeezing is not a unitary operation, by the way, but this is also an operator like this, e to power something. So you just focus on the exponent. So if you focus on the exponent, you see a dagger square and a square. So these are the creation annihilation operators of those photonic states. So you are either annihilating two photons or creating two photons. So it's a two-photon process. So you need some nonlinear optics for generating these squeezings. That's not the only way. In our research, we are also playing around with optomechanics, and you can generate squeezing with amplitude modulation, frequency modulation. So there are various ways that you tailor these Hamiltonians. Okay, but let's go with the standard way. You can calculate these. If this is the squeezing operator, you can calculate these standard deviations, which come out in this form. This is another part of the homework. This is not easy. You should play with these Baker, Campbell, Hausdorff lemmas and those things, which is very standard in quantum optics. And you can find this in any decent quantum optics book. What it does is it squeezes in that direction. Okay, for instance, this value of phi. Phi is the phase of the squeezing parameter. Okay, so the squeezing parameter, we'll see what it is in a concrete example, the squeezing parameter. But it can be the modulation depth of a amplitude modulated laser, for instance, or in here, it will be some concrete parameter in the parametric down convolution. Okay, so if this phi is 0, in that case, this minus sign is a true minus sign, and this is squeezed. If phi is pi, this is reversed, and this is squeezed. So depending on that phi, you can squeeze one quadrature, another quadrature, or somewhere in between. Okay. So if you are say, I want to know the position of the mirror, LIGO experiment. I don't care about the momentum. Then you can really squeeze the position degree of freedom and make a very precise measurement. Okay, so squeezing in that respect is valuable if you can sacrifice the other non-commuting operator. So how would you generate squeezing? As I said, it requires two-photon process, which Ozan Hoca mentioned. It's a Chi2 process. You have a pump laser, and out of this crystal, you have two photons that come out at half the frequency, whatever. And the Hamiltonian is so easy. You eat one pump photon, annihilate this, and you create, there's a dagger left over here. You create an idler and a signal photon, and Hermitian conjugate must also be there because this has to be an observable, so it must be Hermitian. So this is the reverse process. You must allow for this, but since you have too many pump photons, but not many existing signal or idler photons, this part of the Hamiltonian will not be very operational. So what you will have here, and if you just have these degenerate Chi2 process, these are the same operator, and you don't care about pump photons. There are so many, you just treat them as a classical C number. Then your Hamiltonian becomes just such a quantity. This is very important, how efficient that process repeats. Usually these are very weak processes, like every 10 to the power minus 5 or so. So we need very efficient of these processes. That's one of the important things in the engineering. But then, if this is your Hamiltonian, then in the time evolution, it's in the exponent. And once it is in the exponent, it's like a squeezing operator, and it is a squeezing operator. So that's how it jumps to the exponent. And then the daily gymnastics of quantum mechanics takes over. Time evolution is just the commutator, and this is very easy to follow this part in the lecture notes, and you can really get these squeezing parameters. What is this U? And U is just some parameter, some frequency times the time you wait for this process. So if you wait long enough, you'll get a very high squeezing. This is just one way of doing this. Okay, so my time is up. Shall I just, or let me ask you to read about non-classical states of light. This is something mentioned in both of those lectures by Sabih Hoca and Ozan Hoca. But please run through these as well. You have Gaussian states with Gaussian Wigner function probability distributions, and the squeeze states, they are still Gaussian, but they are in a sense very non-classical. These signal and idler, they are actually entangled pieces. Other non-Gaussian states, again, Sabih Hoca nicely mentioned these in number squeeze state and anti-squeeze phase. You can also produce macroscopic superpositions of photonic states, a laser light, and you just, if you can, create these macroscopic superpositions like this. Okay, this guy plus this guy, preserving this phase, and you can so-called produce cat states, but they are very fragile, and you can even produce superpositions of superpositions, such higher order cat states. But as I said, you cannot protect them long enough against the environmental agitations. Yet another very useful metrologically state is null state. You can have two channels, all the photons in one channel, no photon in the other channel, and superposition of vice versa. And this phase is so important. If you have so many photons in this contrast, then metrologically your phase is amplified that much. So these are very important in quantum metrology in reaching the Heisenberg limit. Okay, people at least on paper have shown how to attain this. And you have, as I said, quantum advantages in sensing, metrology, and all other fields with these non-classical states, including squeeze states, which are Gaussian, but they are they have quantum advantage. Okay, so that's it.
Okay, thank you very much for your presentation, Professor Ceyhun. Thank you very much.